In this video we're going to look at sequences and series. Sequence is a set of terms in a definite order where the terms are obtained by some rule. So there's different ways of giving this rule, as we will see in this video. So a finite sequence ends after a certain number of terms. An infinite sequence is one that continues forever, so it continues for an infinite number of terms. Consider the infinite sequence of the odd numbers 1, 3, 5, 7, 9, 11 and so on. You would say U1 would be your first term, U2 would be your second term, U3 would be your third term, and so on. Un would be your nth term, or your general term of the sequence. To determine the formula for the nth term, we examine the difference between each successive term, and a constant difference suggests a linear sequence. So that's an easy thing to look for. So let's look at a wee example on that. So in this one it says, find the nth term of the odd numbers. So if we just write out a few of the odd numbers and see what we can find. So your first odd number is just going to be 1, and then we've got 3, then we've got 5, then we've got 7, then we've got 9. I'll just do a few. And the common difference to get from here to here, so from 1 to 3 you add on 2, from 3 to 5 you add on 2, from 5 to 7 you add on 2, from 7 to 9 you add on 2. So this tells you that there is a 2n involved. Okay, now the easiest way we have then to find what, we'll test out first of all to see if 2n works. So 2 times 1 gives you 2, but your first term is not 2, your first term is 1, so that has not worked. So you can do it by inspection. You could say my nth term is equal to 2n, and our first term was 1, so 2 times 1 was 2. So you have to do 2 minus 1 to give you the 1. So that would be 2n minus 1. So you can test that out. So we'll pick this term, the 7. If you look at the 7, that is my fourth term. So let's just check that it works. 2 times 4 is equal to 8, and minus 1 gives you 7. So you know that this does work. Okay, another way we could do that without doing the awkward inspection thing that I've just done there is go back to the first term, which was 1, and then we're going to go back on ourselves. So the term previous to this one, if I went back, this term would have been 1 minus 2, so it would have been minus 1. And notice minus 1 is what you have over here. So that's another way that we can do that. I'll show that again in another example later on. Okay, a couple of things to look for. It's not always going to be a linear term. But one thing to definitely look for is look at the differences. Is the difference constant? Then it is going to be a linear term. And then you compare with your basic n squared, n cubed terms and see if it's a quadratic or a cubic sequence. And then you look for power sequence. So this one, for example, it's 1, 2, 4, 8. So to get from the first term to the second, I multiply by 2. To get from my second to the third, I multiply by 2. So this is going to be 2 to the power of something, this sequence. And last thing is, do the signs alternate? So if it goes minus, here it is minus, positive, then there will be a minus 1 to the power of n involved. It may not be minus 1, it may not be minus 1 to the power of n, it may also be minus 1 to the power of n plus 1 or n minus 1, and we'll see in the examples you may have to just play around with that a little bit. Okay, in this, we've got 6 examples here. We've got to find un, or the nth term as we're more used to saying it. Here in the first one, this is an example where the first thing I notice is I have got the same common difference. So I'm adding 3 every time. That tells me there's a 3n involved. And I'm going to use the new way of doing this, in which I'm going to go back and find out what term would have been before the 5, the first term. So if you went back 3, what you would get, it would be 2. So that means my nth term is just going to be 3n plus 2. I'll not say nth term, I said un, so un is equal to 3n plus 2. Okay, the next one, let's have a look first of all and see if there's a common difference. We've got, it goes up in 3s, then it goes up in 5s, then it goes up 7s, and then it goes up in 9s. So it is not going to be a linear sequence, so unfortunately we can't do the method I've just done in my part A. Okay, I'll get rid of that, that's not going to work for us. Now, what I do know is my nth squared term. My nth squared term is going to be equal to, just write it down, sorry, nth squared term is going to be equal to 1, 4, 9, 16, 25. Now let's compare this with what we have in this sequence. We've got 1, here we've got 2, we've got 4, here we've got 5, we've got 9, here we've got 10, we've 16, here we've got 17, 25, here we've got 26. So our term is very close to the nth squared term, but it's not quite. It is n squared plus 1. Okay, next one, let's have a look at what's going on here. I go 2, then I double it, I go to 4, I double it, I go to 8, I double it, I go to 16, I double it, I go to 32. So that means it is my power series. So my un is going to be equal to 2 to the power of n. Now let's just check that works. First term, 2 to the power of 1 is 2, so that works. Let's just do the fourth one, 2 to the power of 4. 2 times 2 is 4, times 2 is 8, times 2 is 16, and that works. So 2 to the power of n is definitely correct. Okay, next one. Let's try it out. We've got 1, then 3, then 9, then 27, then 81. So to get from the first term to the second, I multiply by 3. From my second to the third, I multiply by 3, and so on and so on. So it's going to be my nth term is going to be un is equal to 3 to the power of n. Now let's just check and see if that works for us. First term, when n is equal to 1, 3 to the power of 1, 3 to the power of 1 is 3, so it does work. So let's go back and see how we can fix that. So this does not quite work. Our first term needed to be 1, so if you'd done 1 minus 1, that would have given you 1 minus 1, that would have given you 3 to the power of 0, and 3 to the power of 0 is 1. So my nth term really is 3 to the power, and the power is n minus 1. Okay, let's just check out, get rid of all that. We'll check my fourth term. So when n is equal to 4, 3 to the power of 4 minus 1 is equal to 3 cubed, and 3 cubed equals 27. So that does work. So that is my nth term, or my un. Okay, next up we've got a fractional term, and these are all just normal fractions are fine. They're not improper or top-heavy fractions. If they were top-heavy fractions, or mixed numbers I should say, if they're mixed numbers you would have to make them top-heavy to be able to do this. We're going to treat this as two separate sequences here. So here on the top line it's just 1, 1, 2, 1, 2, 3, 4. That is just my n sequence. That's my sequence of numbers. Just the bottom line, I've got 4, 9, 16, 20, 25. So that really is going to be, it's an n squared sequence. And let's just see, does n squared work? 1 squared is 1, 2 squared is 4, so it's not worked. So we're going to have to change that a little bit. That's not quite right for us. It's going to be brackets n plus 1 all squared, and that will work for us. Okay, in this last example here we have got what's called an alternating sequence. It goes positive, negative, positive, negative, positive, negative, positive. So we have to work out what is going on. The sequence itself, we're going to do this in 2 bits. We're going to sort out the positive and negative, but first we're also going to sort out what the numerical part of the sequence is. So we have got our un, and we've got 1, 4, 9, 16, 25. I noticed I didn't mention positive or negative. I don't really care at the minute. We're just looking at this sequence. This is my n squared sequence. Okay, so this is going to be involved in the answer. And next part I'm going to do is sort out the positive negative thing. So it said in our notes we do minus 1 to the power of n, and I said we need to sometimes play around with that a wee bit and see. Okay, our first term was positive 1. So when n equals 1, 1 squared first of all gives you 1, happy days, but minus 1 to the power of 1 gives you minus 1. So this bit, if you left it as it was, that would give your first term being negative, so it's not quite right. So what we can do, we can change the power from being n to either n plus 1 or n minus 1, and it doesn't make a difference. They both will give the same thing. I'm going to just do n plus 1. Okay, let's just check that again. We'll just say when n is equal to 1, your u1 is equal to 1 squared times minus 1 to the power of 1 plus 1, which is 2, which is just 1 times 1, which is 1. So that works. Let's check another one. We'll just check 3. We'll not check 3. We'll check one of the odd ones. We'll check 4. And so when n is equal to 4, u4, my fourth term, is equal to 4 squared times minus 1 to the power of 4 plus 1. 4 plus 1 is 5. So that becomes 16 times minus 1, which is equal to minus 16, which does work. Okay, what we've been looking at so far are sequences. We're now going to add the terms of the sequences together, and once you add the terms of the sequences together, you get what's called a series. So when the terms of a sequence are added, the sum of the terms is called a series. In a finite series ends after a finite number of terms, and an infinite series continues indefinitely. So the Greek letter sigma is very important, so sigma here, and it is used to show that the terms of sequence are added or are to be added. The symbol can be interpreted as a sum of. So here, this means a sum of all the UR terms. So here, this means the lower part of it. It's a bit like your integral notation. So remember, if you integrated from 1 to 5 of x squared with respect to x, that means you're integrating between x equals 1 and x equals 5 of x squared. So here, this means you're summing up from r equals 3 to r equals 7 of my UR sequence. Okay, so there you can have, you see you've got the u3 plus u4 plus u5 plus u6 plus u7. Example 1 says, write the sum 1 plus 2 plus 3 plus 4 all the way up to 100 using the sigma notation. There are loads of different ways you could do this. So this gets started. I'll show you 2 of these. This is the sum, clearly just the sum of the numbers, the n series of numbers, so just the natural numbers being added up. And we start with n is equal to 1, and we finish with n is equal to 100. The way I've written it here isn't normally written this way. You don't normally say what the n is at the start, or at the end, sorry. So n is equal to 1, the sum of the n numbers from n equals 1 up to n equals 100. Or you could say, so we could write that slightly differently. It is the sum of r from r equals 1 to 100. Doesn't make a difference. Okay. Next one, it says write the sum of 1, 4, 9 all the way up to 100 using the sigma notation. Okay, this one is, it's clearly I'll use the r this time, it's my r squared series. So it's sum of that from r is equal to 1 up to, and a common mistake people would make here would be saying it's up to 100, but it's not. You think what 100 is? 100 is equal to 10 squared. So really it's a sum from r equals 1 up to just 10. Okay, this question says calculate the sum of just a set of r numbers from 1 to 10. So I'm going to do this 2 ways. Show you a couple of ways we do this. You could just go out and just go 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. I haven't told you otherwise. You could do that and you would get 55. Another way of doing it, let's just see how we could do that. So I'm going to look at that sequence again. I'm going to write that sequence out again. I'll just do that now. I'll pause the video and do that. Okay, so I've just written that sequence out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And what I'm going to do now is I'm just going to write it out again, except underneath, except in reverse order, just to show you a nice wee trick for doing this. Okay, so here we have the numbers. We have got 1, 2, 3, 4, 5 all the way up to 10. We have 10, 9, 8, 7 all the way down to 1. Now if we look at these things as pairs, we have got this as a pair of numbers, another pair, and so on all the way along. I'll just do the last 2. And what do each one of these pairs add up to? They add up to 11. So 10 plus 1 is 11, 9 plus 2 is 11, 8 plus 3 plus 8 is 11, and so on. So here, what we have is we've got our total, or our sum I should have said, is going to be, we've got 10 lots of numbers worth 11. But that's that's me counting up the numbers 1 to 10 and then 1 to 10 backwards again. So I need to divide by 2. So let's just do that and see. That's going to be 10 times 11 is 110. Divide by 2 is 55. Okay, so say the question said find the sum of from, let's say n this time, n equals 1 to n is equal to 100 of n. You could just do, it's going to be 100 times 101 and then divide by 2. So to save you multiplying out all the numbers, just do 100 times 101 and then divide your answer by 2. Okay, this example says write out the terms in the series and hence calculate. So we have r squared, and it's from r is equal to 1 to r is equal to 4. So that's going to be 1 squared plus 2 squared plus 3 squared plus 4 squared. And if you add those all up, that's just going to be 1 plus 4 plus 9 plus 16. The 4 plus the 16 gives you 20. 1 plus 9 gives you 10. 20 plus 10 gives you 30. This example says write the sum 1, 2, 4, 8, 16, 32, 64 using sigma notation. So the first thing we need to figure out is what the nth term of this sequence would be, and it would have been 2 to the power of r minus 1. Because if you look at your first term, sorry, we could do this different ways. I've done this starting with r is equal to 1, so that goes up to 7. So let's just check if that's right. This one would be my fourth term, so r would be equal to 4. And 2 to the power of 4 minus 1 is 2 to the power of 3, which is equal to 8. So it does work. So that's what you would have. Another way you could have done that one, you could have just said it's just 2 to the power of r, and then played around with your limits. So that was from r is equal to 0, would be my first term. So that's 0, 0, 1, 1, 2, 3, 4, 5, 6. So that's what you would have as well. And both are equally good. That's correct, and that's correct. It just looks a little bit different. Okay, next one, it says write the sum 1 plus a half plus a quarter plus 1/8 plus 1 over 16 using the sigma notation. I'm going to just change how we've written these a wee bit. That really is 2 to the power of 0, and that is, oh sorry, it's a plus series. That's going to be plus 2 to the power of minus 1 plus 2 to the power of minus 2 plus 2 to the power of minus 3 plus 2 to the power of minus 4, and so on. So what we have really, that's going to be 2 to the power of r, I'll say minus r, and that's going to be from r is equal to 0, and then it goes on, dot 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 shows it goes on forever, so infinity, so your wee infinity sign on the top. That's it. Example says write out all the terms of the series. So it's sigma from r is equal to 1 to 6 of 2r plus 1. So my first term, putting in r equal to 1, I'm going to have 2 times 1 is 2 plus 1 is 3. My next term is going to be 2 times 2 plus 1 is going to be 5. Next term is going to be 2 times 3 plus 1 is 7. Next term is going to be 2 times 4 plus 1 is 9. Next term is going to be 2 times 5 plus 1 is 11. And my last term is going to be 2 times 6 plus 1 is going to be 13. And that's it. You do not add them all up, just to give you a numerical term, because this shows you all of the terms. Okay, recurrence relations are another way of giving sequences and series. Recurrence relation defines the first terms in a sequence and the relationship between successive terms. So the most famous one of these is a Fibonacci sequence. So the Fibonacci sequence is 1, 1, 2, 3, 5, 8, and so on. So if you were to define the Fibonacci sequence, you would need to state what the first term is, you need to state what the second term is. So the first term is 1, the second term is 1, and then you would need to state how you get the rest of the terms. So the rule for getting the rest of the terms. So to get my un, I could say, I add my un minus 1. So if this is my term, my un is the term that I'm looking for. It's equal to my previous term plus my term before that again, so un minus 2. Okay, so that means to get my u3, for example, my third term, it's going to be equal to u2 plus u1. So it's going to be 1 plus 1 so it's equal to 2. To get my u4, it's going to be equal to my u3 plus my u2. So it's going to be, what was my u3? My u3 was 2, so 2 plus 1, so it's going to be equal to 3, and so on. Okay, just to show us there's different ways we could write this. We could change lots of things here, but I'm just going to change these wee bits in my u here. And this is going to be here. I'm going to write this one slightly differently. So I'm going to say, to get the term 2 involved, I'm going to have my un plus 1 and un. So that means exactly the same thing. So the term that I'm looking for, if it's un plus 2, then it's equal to un plus 1 and un. So it means exactly the same thing. I prefer the other way of writing it, but they're just as correct. The other thing, if you change the Fibonacci, the starting point in the Fibonacci sequence, you would get a completely different thing. So if these first two terms weren't 1 and 1, then this Fibonacci sequence would look completely different. Okay, we're going to look at this example here. I'll just clear what I... Okay, first example here is state the recurrence relation for the sequence. Bit of a strange one here. Not really any need to use a recurrence relation for this one, but they've asked for it, so let's go for it. So here, my first term is 5, so you've got to state what your first term is. And then how you get from the 5 to the 8 is you just add 3, and how you get from the 8 to the 11 is you just add 3, and so on. So it's really just a linear sequence, so this is not the best way of doing it. But again, they've asked for it, so we have to do it their way. So my un plus 1 is equal to un plus 3. That's all it is. So to get this, the term that you want, it's just the previous term plus 3. Another way, which I would prefer to say it really is, un, which I say that's the term that I want, is equal to the previous term plus 3. So whatever one of those you prefer. Okay, it says find the first 5 terms of the sequence defined by the recurrence relation. So the recurrence relation is this, and also you've got a starting point here. So my u1 is equal to 3, and that's what one of the bits they've asked for, so you have to write that down. My u2 then is going to be equal to, so if this bit is equal to 2, then if un plus 1, or n plus 1, sorry, is equal to 2, then n is just going to be equal to 1, so that's just u1 plus 4. So u2 is just going to be equal to 3 plus 4, so u2 is going to be equal to 7. Same idea, u3 is going to be equal to u2 plus 4, so u3 is going to be equal to 7 plus 4, so u3 is going to be equal to 11. u4 is going to be equal to u3 plus 4, so it's going to be equal to 11 plus 4, so it's going to be equal to 15. And the last one we have to do, u5 is going to be equal to u5, sorry, is equal to u4 plus 4, so it's going to be equal to 15 plus 4, so it's going to be equal to 19. Okay, this example says the recurrence relation is defined by the formula un plus 1 is equal to a upon un plus b. Given that the first 3 terms are 3, 4, 6, find the values of a and b. So my first term, first of all, it tells me is equal to 3. So that means, and my second term, sorry, is equal to 4, and my third term is equal to 6. So to get my u2, my second term, it's equal to a times my u1 plus my b. So fill in what we know. So we knew u2, the second term, was 4, is equal to a times my first term, which was 3, plus b. I'll just write that a wee bit nicer. That's going to be 4 is equal to 3a plus b, dot, 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 equation 1. You can probably guess where we're going with this. And also my u3 then would be equal to a times u2 plus b. And again, fill in what we know. u3 was 6. My u2 was 4, so that's going to be 4a. And my b, we don't know, dot, 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 equation 2. Okay, we have two unknowns, two equations, two unknowns. So we'll just write those down again. We have 4 is equal to 3a plus b. That was my equation 1. We have 6 is equal to 4a plus b. That was my equation 2. I always just do the top one minus the bottom one, so that's just going to be 1 minus equation 2, which is just going to be 4 minus 6, which is minus 2, 3a minus 4a, which is minus a, and b minus b, they cancel out. So you've got minus 2 is equal to minus a, or a is equal to 2. Put that back into equation 1. You're going to have 4 is equal to 3 times the 2, which is 6, plus the b, or minus 2 is equal to your b. b is equal to minus 2. Okay, and just for neatness, really, I would just tidy it up at the end, and I would say, therefore, your un, I haven't really asked you for this, but I would just tidy it up as well. Now, un is equal to 2 times un plus, oh, sorry, minus, that should be a minus, minus my 2. That was n plus 1. un plus 1 is equal to 2 un minus 2. Okay, folks, you're now ready to do the sequence and series questions, exercise 1 and also exercise 2. Any problems, please get in touch.